Okay, so good evening and welcome everyone to another online session of Astronomy Untitled Leiden. And today we are very glad to have you all here, and we are very excited to share with you some interesting program. And today we have speakers Zocchi and Stella Reino, who will be telling us about stellar streams and globular clusters. And yeah. So for those who are new here, Astronomy on Tap started in New York City in 2013. And it's an initiative where astronomers and educators give talks about how their works on astronomy. We also have fun games and quizzes. So Astronomy on Tap Leiden is the first of its kind that started in Europe, and it started in 2017. We do Astronomy on Tap Leiden on the last Monday of every month. We usually do it at the Burg here, but because of the coronavirus situation, now we are having it online. Currently, there are over 40 locations all over the world where Astronomy on Taps are happening. For today's session, we have Anik here as the question moderator. We have Marta, who will be hosting the games. We have Andres as the tech support, and we have Alice and Stella as speakers. So for today's stream, we are having it on YouTube. As you can see, you can always leave questions for the speakers or for us when the talks are happening in the live chat. During the talk, after the talk, we have a moderator who will ask the questions and pass it on to the speakers for answers. Yeah, so let us know in the chat if you're watching and interact with us in our social media. Take a selfie with the stream and or your beer. Here are some examples from our previous events. And yeah, that's very nice to interact with all of you. And for our social media, here you can see all our social media channels, our website, our Facebook page, Twitter, Instagram, and email. So feel free to interact with us through all these medias. Yep, moving on to the astronomy news. I am sure that at least some of our viewers are already acquainted with the news of this month. This is the Neowise comet that was widely visible almost throughout the whole month of July. In the northern hemisphere, and it's actually one of the brightest comet that is visible at the northern hemisphere after the Hale-Bopp comet that came at around 1997. So it's it's a long period comet. That means that it comes back near the sun after a very, very long time. So it will come back near our sun after 6,800 years ago. It was first discovered on March 27 by the astronomers the Wide Field Infrared Survey Explorer, or the WISE Space Telescope. And yeah, we are seeing it pretty much all the time at July. Since July 24th, it is getting fainter and fainter, but if you are lucky, have a dark place and a pair of binoculars, you can still look for it. Here, you can see two pictures that were taken by our colleagues from the observatory, and these are just taken for fun, but yeah. I hope if you have taken pictures, feel free to share with us in our social media or tell us about it in the comments. Yeah, for today's program, we'll have first the talk about looking at all stellar clusters with Neowise by Alice Zocchi. Then we will have our quiz and games. We'll have a short break after that. And then we will have our second talk by Stella Reino about stellar streams, a trail of clues left by shredded stellar clusters. And afterwards, we'll have the answers to the quiz and declare the winners, and then we'll conclude the night. Now, before our first talk, let me introduce our first speaker, Alice Zocchi. So here she is now working as a postdoctoral researcher at ESA, at ESTEC ESA, and she did her bachelor's, master's, and PhD from University of Milano. So it's her true alma mater. And afterwards, she moved on as a Newton Research Fellow at the University of Surrey. And then she worked as a postdoctoral researcher at University of Bologna. And here, as a fun fact, she worked as she was a scout even 10 years ago, and she remembers the Morse code by heart even now. Here you can see her in this cute red hat in the middle of her scouting team. So yeah, welcome to Alice.
Hello. Hello, everyone, and thank you for being here. It's a pleasure for me to talk about stellar clusters because they are my passion. I work my research is about stellar clusters, and I think that they are the prettiest objects in the universe. Stellar clusters, in particular, the ones that I will talk about tonight, are globular clusters, which are very old systems, and they are very dense. And as you see in this image, in the very center, they are very bright because the stars are all packed together very, very closely. These systems are old, are among the oldest objects that we have in the universe. And the density in the center is so high that if the Earth were to orbit one of the stars that are in the center of these objects instead of our sun, we would be able to read a book by the light of the night sky, which is pretty nice. And I think that, however, I prefer in our nights, the nights that are dark. And if we want to light up a light in our night skies, we would have to gather around a campfire. And this is something I really liked when I was a scout, to gather around the campfire with my friends. And some nights we would tell stories around the campfire. And this is something that I really liked. And I particularly liked when older people were telling me stories about before I joined the Scouts, and about when they were young, because in that way I would learn about them and I would understand them better in the present day. And this is something I am curious about, also not only about people, but about the universe itself. So it would be nice to know what happened in the universe when it was young, what happened before we were born, and in the past. The problem is that nobody was there around to be able to tell us, really. And so we would be needing to talk to someone who was around, and globular clusters were actually around. So we should ask them. And they are actually able to tell us stories about the young universe. And how do they do that? Well, they do that by telling us how their stars are distributed. So by the way, the stars are distributed in a star cluster, we can understand how it formed and how it evolved. And we can have clues about its past. Another important clue that we can have is how are these stars? So how bright they are, what are they made of, how are they distributed, how their composition changes with respect to the position that they occupy in the cluster. And my favorite, they tell us stories also about how they move. So by looking at how stars move within globular clusters, we can have an idea of what brought them to be the systems that we see today. And by looking at this, we can, so if we gather all this information, we can try and answer some questions that are very important and that for which, whose answers I am really curious to hear. So in particular, by looking at all these clues from globular clusters, we could be able to discover how they formed and how they evolved, and not only about them, but also about their host systems. So globular clusters are tight groups of stars that are held together by their own gravity, so they attract each other thanks to their own mass. And they live in galaxies. So in our Milky Way, we have 150 globular clusters. And in other galaxies, there are even more. So by looking at the population of globular clusters in the galaxies, we could probably get a clue about how they came to be, and also about how the galaxies themselves formed. And another thing is that because globular clusters are so old and they formed when the universe was very, very young, they can maybe tell us something about how the universe was in that moment. So how was the environment that brought to their creation, to their formation? The problem is that for a very long time, scientists have tried to ask these questions to globular clusters, to try and interrogate the stars and their movements, to try and answer these questions. But after a while, they thought that globular clusters were actually pretty boring. And that's because the answers that they were giving to these questions were not exactly what they were not exactly very exciting. And let me tell you why. It's because it turned out that globular clusters seemed to be very simple stellar systems. So they were very often described as having a simple geometry. So they look like roundish, so they could be described like spheres, like with spherical symmetry. So nothing fancy going on there. They also could be described as having simple dynamics. So having, for example, no ordered motion, so without considering rotation of all the stars together, so no ordered motion of all the stars moving in the same way. And it was considered that every stars had the same possibility to move in each direction, and that we can call isotropy of the velocity. So every direction of the velocity was possible. And most importantly, they were considered to be the prototype of simple stellar populations. So here on the right, you see a color magnitude diagram. And the color magnitude diagram means that we have a color on the horizontal axis and the brightness on the vertical axis. And we use this diagram, astronomers use this diagram to see in which phase of their evolution the stars are. And in this case, you see this line over here, it's an isochrone. It means that it represents the line where stars align when they have the same age. So if you take a stellar population and you let it evolve for 13 gigayears, so 13 billion years, like the age of globular clusters that we see in the galaxy today, you would get something like this. So stars aligning to this line. And in this plot, you have brighter stars that are in the top and fainter stars in the bottom. And then you have blue stars on the left, which are the hottest, and red stars that are that are colder on the right. And so the idea was that globular clusters are simple stellar populations, so their stars would align with this line. And actually, for many, many years, there was a kind of a race to get the perfect global color magnitude diagram with the narrowest sequence in this diagram. And so, if this is the situation, so we have we see that globular clusters, we saw that globular clusters were simple, so with simple geometry, simple dynamics, made of simple stellar population. Does it mean that there is nothing more to learn from them? Well, this is actually what it was considered the truth for a very long time. So about 30 years ago, people thought that, yeah, that's it. We know everything we have to know about globular clusters. They are not interested anymore. We know that they are simple. We understand why they are simple. That's it. Let's move on. But actually, the situation is not really like that. It's like looking at a painting. Like, look at this painting, for example. If you look at it long enough, you will be able to count how many squares it is made of. You will be able to describe the colors. And in a while, you will be knowing it by heart without the need of observing it anymore. So you would know everything there is to know about this without the need to investigate further. Because let's face it, a painting like this is not really exciting. It's pretty boring. But what happens if we have a better resolution? So this painting is not like this, it's like this. It starts to become more interesting. And what if we have even more resolution? Or even more? Then we discovered that this painting is indeed the Sterrennacht by Van Gogh. And by looking at this, actually, we see that there is a lot of complexity in this painting that was not captured by the first set of squares that I showed you. So by looking at the painting like this, we would be able to look at all the colors to try and understand which part of the painting were painted before and which later, and what are the various layers that are in the painting. So by looking into this, we would be able to really discover a lot. So there is a difference between the first type of image of this painting that I showed you and this one. And it's that we are looking at it like this with new eyes. So we have a much improved vision with respect to the first image that I showed you. What if this is actually what was happening with globular clusters? What if there is more there to discover? And the culprits, it's not that the globular clusters were boring, but it's because we were looking at them with the wrong eyes in a way. Well, actually, it's true. And we know that this is true because there have been two space telescopes that have driven a revolution in this topic. The first is the Hubble Space Telescope. Here you see an image taken with the Hubble Space Telescope of one of the globular clusters in the Milky Way. And you see that thanks to this image, you can actually see a lot of stars. You can see stars with different colors. You can actually kind of see that the blob in the center is not all connected to each other. So it's made of single stars that are moving around here. And this is actually something that the Hubble Space Telescope is great at, looking at very, very dense regions. For example, this one. This is the center of the globular cluster Omega Centauri, which is the most massive among the globular clusters in the Milky Way. And this image was taken by the Hubble Space Telescope. And with this image, we are looking at many, many stars in the very, very center of the cluster. So there are stars with different shapes, in the sense that some are bigger, some are smaller, some are brighter, some are fainter, and there is a lot of difference in this picture. It's much more rich than what we would be able to see if we would see just a blob, a bright blob in the center of the cluster. So with this, we can really see the discreteness of the stars, and we can discover and learn their properties a little bit better. And by combining the Hubble Space Telescope with the ground-based observations of spectroscopic observations, it was also possible to look at the compositions of these stars. And scientists discovered that the compositions of these stars are not always boring as we would expect, but there is something going on there. There are some differences among stars that are not really clear. It's not clear why they would be so different. Also, another thing that thanks to the Hubble Space Telescope was possible is to measure proper motions of stars. It means that you could measure how much stars move. And this is done by taking images taken apart in time. So you take an image, you wait for 5 or 10 years, you take another image of the same area of the sky, and you see how stars have moved in the meantime. And Hubble was the first telescope that allowed to make measurements of this kind very, very precisely, and which was very great to study the internal dynamics of stars. One thing, though, that it's not possible to do is to measure ordered motion in this way. Because if you take two images and then taken apart in time, and then you subtract them in a way from one to another, you look at how the stars are differently distributed from the first to the second, you erase the ordered motion. So you will not see if two stars are going in the same direction with respect to the rest of the sky. But you would see if they are going apart or if they are going closer to each other. So you would see the relative motion of the stars, but not if they are moving together in the same direction. And this means that we are able to measure the chaotic motion inside the clusters. So if stars are going closer or farther apart from each other, but we cannot measure, for example, the rotation. And actually, this is true for all the clusters in the Milky Way, except for one, which is a lucky one. But this is another story. So what happens? It means that we cannot measure rotation for clusters. Well, no, we have another telescope that is helping us to do that. And it's Gaia. The Gaia telescope is a mission from the European Space Agency. And so Gaia is a telescope that is looking at the sky. It's scanning the entire sky. So here you see an image that was released with the first data release of the data of Gaia. So you see in this image the Milky Way. You can clearly see the plane of the Milky Way in the center. You see the large Magellanic Cloud, the small Magellanic Cloud, and everything that you see bright in this image is a star. So it's a map of all the stars that Gaia was observing, has observed up to the first data release. And because Gaia is looking at the entire sky, it means that it's also looking at all the globular clusters in the Milky Way, which are these red points that you see in the image. So for all of these points, Gaia is looking at their own individual stars. And for the closest ones, it's measuring very, very precisely the positions of the stars, their distance from us, and how they move on the plane of the sky. And this is particularly great because then it means that Gaia is looking at the entire sky altogether. And so it means that when it measures motions are absolute motions. And so in this case, we can really measure the rotation of clusters and any ordered motion that these clusters have. So we can also measure their orbit around the galaxy and what path they are following. And if you're curious about orbits of clusters in the galaxy, stay tuned and make sure you listen to Stella's talk. So another thing why Gaia is really important, and this is just one example, but there are many for which, I mean, it's my favorite telescope for a reason. It's this one. So you see here, these are all the dots that you see in this image are stars. And I am actually showing here the positions as they are measured by Gaia. So these are Gaia data, and you see in gray the stars that are foreground stars or background stars, and in red you see stars that belong to a globular clusters, to one of the globular clusters of the Milky Way. So this image is particularly striking to me because this black line that you see here, this semicircle that you see here, is basically what we thought it was the edge of this cluster. So the further boundary of this cluster. So before Gaia data, we thought that that was the edge of the cluster, that nothing was going on outside it. But with Gaia, Gaia produces data that are also useful to group stars together. So it measures velocity, as I said, it measures position, but it also measures the brightness of stars and their color. And so by clustering together, by grouping together all the stars that have the same properties, you can find stars that belong to the cluster, even if they are farther away from their center than you would imagine. And also it's great because then in this way you can really disentangle which stars are the stars that belong to the cluster and which stars are actually stars that are in the foreground, so or in the background, so they are further away from us than the stars of the cluster, and so have nothing to do with the cluster but happen to be in the same line of sight when we look in the sky. Okay, so that means that with this new data, with these new eyes that we have, we cannot really keep this picture like this anymore. We have to fix it. So globular clusters are not simple. They are very complex. There is a lot of things going on. There are a lot of things going on. So there is really a lot more to learn from them. So just to give you an idea of what we actually discovered, thanks to the Hubble Space Telescope and Gaia, and also thanks to the many surveys that have been carried from the ground in the last few years, we now know a lot of complexity, that there is a lot going on in these systems. They are very complex and very rich. So we know that actually their geometry is not really as spherical as we thought. So they show a little bit of flattening. They are a little bit elliptical. They are not perfectly round. And the reason for this flattening is not being explored yet. So it is interesting to look and try to understand why they are so, their morphology is like this. We know that they interact with their host galaxy, so they are not alone in the void, but they belong to a galaxy that has a mass and a gravity, and so their interaction with this galaxy creates some features that can be observed. the velocity is not actually as isotropic as we thought. So in some cases, there are preferential directions for the motions of the stars. In particular, a lot of clusters have a preferred radial direction for the motion of the stars. So the stars go from the very center of the cluster out to the periphery and then back. And this is a radial anisotropy. So it's called. Then we know that some clusters rotate, so there is a motion of an ordered motion of the stars that do rotate around an axis along the line of sight or on the plane of the sky, and this can be disentangled with different types of data. Then we know that there is mass segregation, and that means that during the evolution of these clusters, because the stars interact with each other, every time there is an interaction between two stars with a different mass, the star that is more massive loses a little bit of energy and slows down. And the star that is less massive gains a little bit of energy and goes faster. And that means that the stars that slow down, the most massive ones, end up sinking in the center. And so they cluster over there and then create a population of massive stars and massive remnants in the center of the cluster. And the light stars go further away and they are distributed all around. Then we know, most shockingly, that globular clusters are not simple stellar populations at all. They have indeed multiple stellar populations. And this is one of the great mystery of this field of research. So we know that multiple stellar populations exist. So that means that if you remember the plot that I showed before, the color magnitude diagram with one single isochron, one single line where the stars were all aligned. Well, now the situation is not like that anymore. There are clusters for which we can see 2 or 3 of those lines together. And so the stars aligning to different of these isochrons within the same cluster. And the reason why this is, it's not totally clear. So we don't know how these multiple stellar populations formed. And there have been several propositions about a possible scenario that could explain this, but still none of them is convincing. And this is very exciting because it means that we have still a lot of things to study and to discover. And then we know that these systems, because they are old, they host the old products of the life of stars. So they host black holes, they host neutron stars, which are very exotic objects that could be found in globular clusters. And by studying the clusters, we could learn a little bit more about them. And also, they host a population of stars that are very weird. They are called blue straggler stars, which have only been found basically in globular clusters. So it seems like the environment that they provide, could be able to create this type of exotic stars. Okay, so now I hope I convinced you that globular clusters are very complex. There is a lot going on in them. But what do we do now? I mean, we know they are complex. We know that there is all of this going on. So what we need to do now is to interpret what we see. So we see a lot of complexity. We need to interpret it. We need to explain it, to try and understand how it came to be and why it is like we see. So why things are like we see them. So for example, we see, and this is what I do in my work. So I take the observations done from these telescopes and try to translate them in quantities that I can compare with models that I can use to describe what is going on in these systems. So, for example, on the left you see isodensity curves of a cluster. So basically what I did there was to take the distribution of stars on the plane of the sky and then do as you do with mountains. So like lines of constant density. So in a mountain, you would draw lines of constant height. And here I did the lines of constant density. So, and if you look at it, it's not round at all. It's actually a little bit flattened and tilted with respect to the vertical axis. On the right, you could see a rotation curve that has been calculated by using Gaia data for the same cluster that is depicted on the left. And so by looking at the velocities of stars, I can try and compute how they move together. And this is the type of rotation signal that we see. So in this case, the stars show that there is some rotation, so they are moving together. So what do I do with this? Well, I use dynamical models to try and explain what I see. So I compute dynamical models. For example, here I show you an example of some rotating models that I am developing. So on the left, you see an example of the flattening that we could produce with these different flavors of these models. So on the left, you see an isodensity curve that is basically spherical. And here on the right, you see an isodensity curved set of curves that are a little bit more flattened. And the difference between the left and the right case, and the middle one is intermediate, it's the amount of rotation that is in the models, which is depicted here in the plot on the right. So you see that the system that is basically round is the one that rotates less, and the system that is more flattened is the one that rotates more. So this is one of the examples that one could use to explain what we do with this data. So I take, for example, I'm very curious to see what is the flattening of globular clusters due to. And so one possibility is that they rotate, and because they rotate, they flatten. And so with this set of models, I try to put these things together, and by comparing this to the data, I will be able to say if rotation is indeed responsible for the morphology that we see in globular clusters. So this was just an example, and it was just to give you a teaser of what is coming. So actually, I just spent a few minutes telling you all about the complexity of globular clusters and how much they could tell us about the universe and the galaxies and how everything formed, but we still don't have the answers. So they still need to tell their story. So here you can see some pictures of globular clusters, which I put there just to show you how diverse they can be and how incredibly beautiful they are also. So my advice is to keep listening to these objects because they have many, many more stories to tell. And I'm sure that the best is yet to come. Thanks.
Thank you, Alice. That was a really great talk. And we actually already have many questions from the audience, so that's great.
Okay.
The first question is from Tuan. And he's asking how far apart roughly are the stars in the center of globular clusters? And if it's so dense in the center, do stars actually get drawn towards each other and do they collide?
Oh, yes, they do. This is the funny part about the dynamics of these systems is that stars can actually collide. They pass by each other. They are very, very close. Now, I don't remember how close in physical units. I will need to go up to look it up. But because I don't want to give a wrong number, but they are very close and they pass by each other very, very often, and sometimes they even collide. And so it is pretty spectacular. And there are a lot of things going on, especially in the center where they are very close to each other. So they could form binary systems, very, very tight binary systems. And sometimes there is a third star that passes by the binary and interacts with the binary. And a lot of amazing things happen because there is a lot of complex dynamics going on. So yes, they are very, very close together and they could even smash to each other.
Okay, then the next question is from Fractalica. How can we find globular clusters in other galaxies?
If you look at other galaxies that are far away, you could see globular clusters there because exactly because they are so dense and so tightly packed. So they are, you can imagine that when these systems are far away, all their stars are basically on top of one another. So instead of seeing one single star, we see a lot. And so their brightness is very, very high. And so when we look at other galaxies, we see some dots that are very, very bright, and those are globular clusters. So they look like very bright dots.
Okay, thank you. Then a little follow-up question on this one. Can any of these internal properties, such as rotation, mass segregation, be detected in clusters outside of the Milky Way?
Yes, in some cases it has been done. You need to use different techniques. So for example, you cannot use Gaia data to do that because those systems are too far away. So with Gaia, you would not be able to measure any rotation or any internal dynamics because you would not be able to resolve the stars. It's like the first picture of the Sternnacht. You would see a square and not everything that is all the paintbrushes within that square. So, but this can be done. So if you take a spectroscopic measurement of these systems, so it means that you measure the spectrum of the light that comes from them, you could measure the velocity of the stars within that. And you will measure the distribution of the velocity. And by looking at the distribution of the velocity, in some case, you would see that part of the velocity is part of the stars are going in one direction and part in another direction, and you would clearly see like a double peak indicating the rotation, the presence of rotation. So this has been done. Yes.
Okay, great. Then the next question is from Ruslan. He says, maybe I missed something. Can you please repeat what happens with that one lucky cluster for which we can see the rotation?
I was hoping to get this question. That's great. Yes. So actually, as I said, the Hubble Space Telescope is taking, to measure proper motions with the Hubble Space Telescope, you need to take two different images taken apart and then basically combine them and see how much the stars moved with respect to each other. And because this is a differential process, so basically you use one star as an anchor to overlap the images, and then you see how all the others have moved. If you do this with one of the stars of the cluster, you cannot detect any global motion. To detect a global motion, you would need something in the background that would be, several stars in the background that are that you could use as your anchor. So the lucky cluster is 47 Tucane. I'm going to show you the cluster. So it's over here actually. And it is lucky because it is close to the Small Magellanic Cloud. So you see, this is the Small Magellanic Cloud. This bright dot over here, it's that lucky cluster. So for that lucky cluster, they used the stars from the Small Magellanic Cloud to anchor the images, and so they were able to measure the rotation of the stars inside it.
Awesome, thank you. Then we have one final question from Damien. There are supermassive black holes. Are there also supermassive globular clusters? And if so, do they have different properties that are interesting or unique?
That's an excellent question. Usually I get the opposite one, in the sense that it has been suggested that because supermassive black hole exists, there could be a smaller version of massive black holes that could hide in the center of star clusters. But having a super star cluster, that would be super nice, actually. And I think that now with the JWST and with the future observing facilities, we would be able to look very, very far away in the universe. And that means very, very far back in the past. And so maybe if any of these superstar clusters exist, that we would be able to see them. So right now, I think that the idea is that supermassive black holes form in nuclear star clusters. So they are related to nuclear star clusters, which are actually even denser than globular clusters and are the clusters that are found in the center of galaxies. Even our Milky Way is one of those. And so these are in a way these super star clusters, but if anything even bigger than that would exist, that I'm not sure right now, but maybe in the future we will be able to see.
Okay, thank you very much. We actually did get another question in, but if that's okay with you, could you maybe answer it on the chat on YouTube? Because I think we have to continue.
Yes, sure.
But thank you for the amazing talk. I think we're all very excited now about globular clusters.
Thanks.
So that's really cool. And then we're going to go continue with the games.
Okay, hello everyone, and welcome to the games. Tonight we've prepared 2 games for you, and this is the form the link that you have to click to go to the Google form to fill in your answers. I think they will post it on the group chat as well on the YouTube page. So the first game is called Observation, Simulations, or Imagination. So we're going to show you a few images, and you have to decide if the image is a real observation of an object in space, B, a simulation, or C, how the artist imagines an object in space. So this is the first image that we have for you guys. Number 2. Number 3. So are these images observation, simulation, or imagination? Number 4. Number 5. Number 6. Seven. We will go through all these images again, so don't worry if you can't decide on one of them. 8. Next one. 10. 11. 12. 14. 15. And the last one. Okay, so game number 2 is called Can You Match the Story with the Satellite? So one of the satellites currently currently working or in the past is going to present itself, and you have to guess which one it's talking. So, question number 1. After they launched me into space, my mirror was deformed, so astronauts had to come and fix me. After my billion-dollar surgery, I made the most beautiful pictures of all. Is it A, Voyager 1, B, Juno, C, Gaia, D, the ISS, E, Hubble Space Telescope, F, Rosetta, G, James Webb Space Telescope, or H, TESS? So which telescope is presenting itself? Number 2, last month I was in the news for making the deepest X-ray sky map ever, which took me 182 days to make. Question 3, I am named after an astronomer and will be the largest and most powerful space telescope once I will be launched in 2021, hopefully. Question number 4, I have been on the hunt for exoplanets almost 2 years already. Together with my astronomers, I have found 1,835 candidates, of which 46 have been confirmed. Question 5, it took me 5 years to travel to Jupiter, where I studied its composition. In almost exactly a year, I will say goodbye and plunge into Jupiter. So which telescope are we talking about? Number 6, I have traveled the furthest into outer space and already left the solar system. I discovered 2 moons around Jupiter and 5 around Saturn. Seven, I aim to make the most precise 3D space catalog ever made. By the end of my mission, my data archive will exceed 1 petabyte of data. And the final one, I was launched in 1998 and have been visited by astronauts many times. When my mission is done, I will be scrapped for parts. Okay, so now we'll go through all the questions again, so you have time to look at any that you didn't manage to figure out at the beginning.
So just to quickly add to this, we saw in the chat that 2 of the questions were missing in the form. They have been added now, so hopefully you can still put in those answers. And otherwise you can reuse the link, another link that has been posted in the chat. So we will go through all of them again, so you have some time to fill it out.
Also, sorry about this. There is a tiebreaker question. How many globular clusters are currently known in our Milky Way? Okay, and now we're going to go through all the questions again for you guys. So remember, for this first game, you have to guess whether the images are observation, simulation, or imagination. On to the second game. And finally, the tiebreaker question. After this, we will go for a short break of about 5 minutes, and you can still submit your answers until the start of the next talk. All right.
Okay, we hope you all enjoyed the very interesting games from today's event and are ready for our second talk before after this short break. So before the talk starts, let me introduce our second speaker of today's event, Stella Reino. Stella is from Tallinn, Estonia, and she did her master's from University College London. Currently, she is doing her PhD at Leiden Observatory, and she's studying the Milky Way galaxy through stellar streams. Now, what are stellar streams? Stellar streams are the remnant of the globular cluster or the dwarf galaxies that are shredded by the gravity of our Milky Way galaxy. In today's talk, Stella will tell us how we can study these stellar streams to understand the size and shape of our Milky Way galaxy, and also how can we extract information about the dark matter content of our host galaxy. Apart from astronomy, Stella is very enthusiastic about musical theaters, and she can sing along to the entire soundtrack of the musical Hamilton. So with that, I'll invite Stella to share her screen.
So let me see. Yeah, all good? So yeah, thank you for having me to talk here. I will indeed be talking about stellar streams today, how they form, what they are, and what we can do with them to learn more about the Milky Way galaxy. But before talking about stellar streams, I will first give you a bit of a brief introduction to the structure of the Milky Way itself. So most of the stars in the Milky Way are on the disk. So these stars usually have just regular circular orbits, so they go around the galactic center. Some stars are also in the halo, but what I mainly want to focus is that this entire galaxy is actually embedded in a big dark matter halo. And how do we know about this? One of the ways we know about it comes from rotation curves. So as I said, that disk stars have mainly circular motion, and what rotation curves are basically is you take the circular speed and you plot that as a function of the distance from the galactic center. So you see what it looks like on the figure on the right hand side here. So the expectation is that the stars that are further from the galactic center should have lower circular speeds, so they should rotate around the galactic center slower than the ones that are more closer to the galactic center. This is in analogy with the solar system, where the planets that are further from the sun rotate slower, and the planets that are closer in are faster. So this is clearly not what we see. If you look at the plot here, the expected blue curve is not what we see when we measure the curve itself. What we find is actually flat rotation curves. What this means, so the expected curve basically assumes that we would have most of the mass concentrated in the center. But the measured curve shows that since the speeds don't go down, which means that there's more matter keeping the speeds higher all through the galaxy. So there must be some matter that we don't see. So the difference between these two curves is what the dark matter halo represents. And I've also plotted here the speed at the solar position. So the sun is around 8 kiloparsecs from the galactic center and rotates with the speeds of around 220 kilometers per second or 230 kilometers per second. Right, so back to the Milky Way. When we want to learn more about the dark matter halo, it's clear that we cannot really go far with the disk stars because the dark matter halo is much bigger than the disk is. So what we have to do is instead look at the stars that are within this halo and see what their behavior is. So one of the things to do is look at globular clusters. Alicia already talked about them, so that's one of the options. Another one that is not in this plot is, but I will add it now, is dwarf galaxies. So these are other smaller galaxies that have been falling into the Milky Way because of the Milky Way's gravity's pull. And they eventually will just merge with the Milky Way. So one interesting thing that can happen with globular clusters and dwarf galaxies is that they can be completely torn apart by the gravity of the Milky Way. So as the stars leave their original cluster, whether it is a dwarf galaxy or a globular cluster, they stretch out in these orbits and appear as big arcs on the sky. So since they are from globular clusters or dwarf galaxies, they are far So they are further than most of the stars in the galaxy. And therefore, we say that they leave a trail of clues for us about the Milky Way's mass, further than just the disk stars. Before I go into the mass determination and how to do it, I want to show you a quick video of how stellar streams are created. So here we see the cluster kind of starting to be shredded. One interesting thing to notice is that the stars are not only falling behind the cluster that they belong to, but they're both front and behind. So there's a leading arm and a trailing arm, shown here with red and blue. Another thing, as it's been torn apart, you see in the green, have been tracing one single orbit. So the stars that have left the cluster still follow orbits that are very similar to the original cluster. So basically they trace out a nice orbit for us to use. So this is important for us because we want to use these orbits to find out more about the gravity that is happening in the Milky Way and therefore the mass of the Milky Way. So let's assume we have this data. We have a stellar stream, and cool, it's a trail of clues. But how do we actually extract this information? So one method that people use is called the orbit fitting method, where we see what an orbit of the original cluster would look like for a particular galactic mass. We then compare the predicted orbit with the real data. And I'm going to give you an example how this is done. So let's say I assume a mass for the Milky Way. This gives me an orbit, and this orbit is clearly not very well aligned with the stream that we have. So orbit is too large, meaning that the gravity's pull is not high enough on the stars, meaning the mass that I've tried to work with here is too low. Now here's an opposite case. The orbit is clearly too tight, which means that the gravity is working too hard and that the mass that we have tested is just too high. And finally, playing around like that, you can get to a perfect match. Well, perfect. So that's all great and it sounds simple, but real life is not as simple as these models. So we cannot always use this perfect example. And it's the reason for that is that the stream stars don't actually follow exactly the same orbit perfectly. So this will be fairly clear when I show you a stream that has more scatter in its positions. So in this case, it is not very clear or not as clear as before which of these ones is best. And of course, when we test it, there'll be more orbits in the middle of these, the ones that are plotted. So just fitting an orbit to the stream data will give us a biased result usually. In my work, I use a bit of a different approach. So now we don't require that all the stars follow the same orbit. We allow them to have different orbits. What we want to see is that they have orbits that are as similar as possible. So we test different Milky Way mass models, and we want to find one that causes the orbits to be very similar. And the similarity of the orbits is determined by a combination of positions and velocities, and we call these things labels. So I will get into that a bit more soon, but basically, the more similar the labels are, the more similar the orbits, which means that we are basically looking for the labels to cluster. But So here I've shown two orbits, the pink one and the blue one. First, I will discuss what is happening on the leftmost figure. So the X and Y plane is basically just the plane of the galaxy, so the motion in the disk. And the Z coordinate is basically just the motion out of disk. So how high it comes from the disk or how low it goes. And R is just a combination of Y and X. So it's the distance that it goes from the galactic center, but only in the disk. So this is clearly not easy to analyze. And we have found that it's easier to analyze the space when we plot these orbits in this space. So here R is the overall distance from the galactic center to the star at each position in the orbit. So it's a combination of this big R and Z, so both the upwards direction in the galaxy and also the distance within the plane itself. And PR here is the momentum in this R coordinate. So it might look a bit weird, but essentially what you're seeing is the behavior of a pendulum. So when the star goes to higher R, goes further from the galactic center, it starts to slow down because the gravity is pulling it. At one point, when it reaches the maximum distance, it comes to a complete standstill, and then it reverses its motion and starts falling back in, and thereby it starts to increase in speed again until it gets to the minimum position and kind of slingshots past through again and starts the motion again. And I think it's also clear that here, why the blue orbit has a larger extent in R. You can kind of see it here that it's clearly covering more space. It goes further from the galactic center than the pink orbit does. We can do a similar pendulum behavior analysis in theta coordinate. So theta, I've shown here what it is. It's an angle that measures this distance from the z-axis. And it's also clear, I think, that the blue orbit has a lower extent here, and the pink orbit goes from a lower theta to a higher theta. So their behavior in theta is the opposite of what it was in R. And how we use these things as labels. We basically just take these loops and we use the area that they cover as the label. So here I've shown the label in R and theta, and I've already said that the R has the blue orbit has an higher label in R. It covers more extent, its area is greater, and the pink one has less of an area here, and it's exactly the opposite in theta. So here we see two stars basically, and the two stars' orbits, and they're not very similar, as we can see here. Now imagine if we had an entire stream. So it basically would mean that we have more data points here. And if we want them to be as similar as possible, as I said before, we want them to basically cluster in the space of these labels. Right. So let's assume that we have many streams. And we want them all to cluster. So we first take some trial Milky Way model. We see how these orbits would end up. And we see that the clusters are pretty spread out here. The labels are not very concentrated. So then we change the Milky Way model until at one point we can focus down these clusters as much as we can to make sure that the streams are really on a similar orbit as possible. And this is what we see. So obviously they don't concentrate to exactly one point, which means that they actually shouldn't be assumed to be on one orbit. So this is the method that we use. Before I talk about what results we get with it, I wanted to mention what kind of streams we actually have even found in the Milky Way. So here's a very short video showing all kinds of streams that we have found. The galactic center is the red dot, red star, and the solar position is this yellow point. So there's quite a few streams, but we cannot sadly use them all in our work because they're pretty far, and we simply can't measure. Well, we haven't yet measured all their positions to such accuracy that we can really make good use of them. Hopefully soon. So I've used in my work four streams. These are called Hilmi stream, Orphan stream, GD1 stream, and Palomar 5 stream. And I've also used them in combination as the previous example showed. So GD1 and Palomar 5, and then all four streams together. It is really important to combine the information from the streams. And the reason for that, besides the fact that you want to use as much data as possible, is that individual streams can give you sometimes slightly incorrect results. And you can kind of see that here that, first of all, their measurements don't always end up perfectly. But when you combine them, you sort of start seeing a consensus. And this is because the streams probe a different area in the space. They are at different distances. They have, like, some go more in Z direction, so higher in the galaxy. Some go to different places. So it's possible that they find a different mass that works for them. And someone in the street is having a party. So yeah, it's important to combine this information so we make sure that we don't take one stream too much into account and bias the result. Right. So, and here is the log of the mass that we find within 20 kiloparsecs. And finally, I wanted to go back to the kind of the beginning with the rotation curve analysis. So with our results, we can get to rotation curves as well. And here I've shown, so this figure is for all the results for all 4 streams. And this one is from just GD1 and Palomar 5 combined. And I mentioned here as well that light shaded regions show all the allowed solutions that we have. Whereas for the dark shaded regions, we have also added an extra constraint that I mentioned in the beginning. So this is from the solar circular motion. We know that the sun is at around 8 kiloparsecs from the galactic center, and that its speed is around 220 kilometers per second. So we just add that as an extra constraint for our models. And we find that we can constrain it even more. And the individual points here are the individual streams at their mean distances. So one thing we can see is that we really need to use more streams that are further away than this 35 kiloparsecs that you see orphan at, and also with much better measurements that allow us to put a smaller error bar here, which would also tighten the uncertainties that we have. But since this is a kind of a new method to be used with, not kind of, a new method to be used with data, so it is right now just like proof of concept, and we will hopefully get more streams and more data and see what where we can get to with this method. Okay, thank you for listening.
Thank you, Stella. That was great. Our very first question is from Lyra. Why do stars get torn from their streams? Is this because of a difference in gravity profile due to the disk of the galaxy?
Yeah, it is exactly. It's kind of the same reason why we get tides on Earth, so that the moon pulls differently on one side of the Earth than the other. So it's the same thing with the gravity of the Milky Way pulling on one side of the stream a bit less, sorry, one side of the original stellar cluster a bit less, and on the other side a bit more. So that is the reason that it is basically torn apart. So it's the tides.
Okay, then another question. Will the results improve with this method if we use as many streams as we have data for? So I think she's talking about the previous one you showed.
Yeah, I think it should, but it's also a question of, do we have good data? Like, how accurate is our measurement of the positions and of the speeds? And also about how, like, everything is a bit limited to what models we offer it. Then I hope that's kind of clear what I mean. So since we test different mass models for the Milky Way, if we don't offer it a good enough model, it cannot give us more information. So it's also kind of a trial and error with that to see what we should be offering it. So there's more to do than just find more streams, but that's definitely one of the things, yes.
Okay, and then we have a golden question. If JWST gets launched next year, will there be more stream data available for this type of research?
Yes, well, I think it will find quite a lot of streams. And in fact, we do already have quite a lot of streams, but the problem with this is that you need the velocities. So pretty pictures on the sky don't really help much. And I don't know if they discover something good and then other telescopes look that way, then it would be great. Because right now, even Gaia isn't enough to do this work. We need Gaia and then some other ground-based telescopes to complement it. So it will discover more streams, but I'm not sure if it'll be useful for this kind of work.
Okay, and then a final question from Raj. How can we trace the kinematics of the SGR stream? Sagittarius, I think.
Tough question. So Sagittarius, I mean, this is something that I've wanted to include in our work, but Sagittarius is, well, it has a lot more scatter than these different streams. Like Palomar 5 and GD1 that I've used are from globular clusters. So the velocities are more similar than they would be in a big like galactic remnant, really, like Sagittarius is. So it's harder to, like, basically in the label space that I mentioned, it would just be huge anyway because it has much more different orbits. Another problem with that is that it has so many stars that I need to do some sort of like, I'm worried that it will overwhelm the rest of the information that we have from other stars. So there has to be some clever way to subsample Sagittarius to be included here, but I really want to. So next step.
Okay, great. We actually have one final question I'm going to squeeze in. What causes the difference between the progenitor orbit and the stellar orbits? Do the properties of the progenitor play a role?
Sorry, say that again. I didn't.
What causes the difference between the progenitor orbit and the stellar orbits?
So, in the most basic way, the stars escape from the cluster in the two, like, further away from the galactic center. So if you imagine the cluster, and the galactic center is here, so they escape from here and here. So within the cluster, they already have slightly higher energies or lower energies. So when they leave it, the cluster, they just kind of end up in this space. At least that's what it's imagined to do. So why they even stretch out is because the ones that are on a higher orbit slightly, they have a longer period. They take longer to go through the entire galaxy. So they kind of lag behind the cluster. And the opposite happens for the stars that are closer by. So that already gives one reason why they don't align perfectly. There are many other reasons that can be due with, for example, interactions with other structures in the Milky Way, like even small dark matter halos that can perturb the streams. Or kick holes into it, basically. So there's multiple reasons. And also, yeah, one of them is the cluster itself. It kind of still has, although in most models we don't use old cluster as a gravity pull, they still do have an effect on the stars that have left. So they still have some sort of a minor effect on that as well.
Okay, great, thanks. We actually did get another question from Damien. But if you have time, it would be great if you can maybe answer that in the chat, because then we get to move on to the game's answers, which I think everybody has been waiting for. So thank you, Stella.
Okay. Welcome, everybody. We are going to go now through the answers for the games. And I believe everyone did extremely well this week, so clearly they were too easy. So the first game is image observation, simulation, or imagination. The first one is an observation. This is an image of Mercury taken by the MESSENGER mission. The second one is imagination. This is an artist's impression of a young planetary system. Sadly, we don't have that resolution yet. The third one is an observation of the small Magellanic Cloud, which is a nearby dwarf galaxy. Image number 4 is a simulation of a supernova explosion, which happens when a massive star dies. Fifth one is an observation. This is a jet of material ejected from the center of galaxy M87. This is the same galaxy that that produces famous black hole image last year. Image number 6 is an observation of dust around a very young star taken by ALMA, an interferometer in the southern in Chile. Image number 7, this is an artist's impression of a collection of galaxies and clusters. Number 8, it's a simulation. It's a simulated collision between the Milky Way and the nearby Andromeda galaxy. It is predicted that this collision will take place in about 4.5 billion years. Number 9 is an artist's impression of two galaxies in the very young universe, when only about 2 billion years after the Big Bang. Number 10, this is the Millennium simulation. This traces the evolution of the dark matter distribution. It took more than a month to run and produced 25 terabytes of data. Number 11, this is a simulation of from the FIRE simulation. The FIRE simulations look at galaxy formation and evolution. Number 12, this is an observation. This is actually done with the data release number 2 from Gaia. It's an all-sky image of our Milky Way, and it's based on measurements of nearly 1.7 billion stars. Number 13 is a simulation of another spiral galaxy from the FIRE simulation. 14 is an observation. This is M51, also known as a whirlpool galaxy. It was the first galaxy to be classified as a spiral galaxy. And you can easily see this with binoculars. Number 15, this is an observation. It's the galaxy M101, also known as the pinwheel galaxy. When this image was taken by Hubble in 2006, it was the largest and most detailed image of a galaxy at the time. And number 16, this is another simulation of a spiral galaxy, also from the FIRE simulations. On to our second game, Can You Match the Story with the Satellite? Our first satellite was the Hubble Space Telescope. And this Hubble celebrated its 30th birthday last April, actually. This is one of the images it has produced, and it contains approximately 10,000 galaxies in here. Number 2 was eROSITA. eROSITA is an X-ray map. It's an X-ray telescope from the European Space Agency. And these two images were one of the first ones it produced. It shows two interacting galaxy clusters. Number 3, we were talking about the James Webb Space Telescope, or JWST. It will be the largest space telescope ever built if it gets launched in 2021. This telescope was originally planned, has been already delayed many times. So let's hope that 2021 is the final one. Number 4, we were talking about TESS. TESS is a transiting exoplanet survey satellite, and it was expected to detect about 1,200 candidates for exoplanets. So it's already passed that expectation. This is very nice. And this is one of the first images it produced. Question number 5, we were talking about the Juno probe. Juno studies Jupiter's atmosphere, its magnetic and gravity fields, and its magnetosphere. And this is an image of Jupiter's cyclones on the South Pole with the outline of the United States superimposed over the central one for comparison. Question 6, this was Voyager 1. This satellite has operated for 42 years, 10 months, and 22 days as of today, and it's still communicating with Earth. It's currently at a distance of 22.3 billion kilometers, and it's the most distant man-made object from Earth. This is the famous, this is the famous pale blue dot image taken in 1990 from a distance of about 6 billion kilometers from Earth. And this little dot in here is Earth. Number 7 is Gaia, which we already know everything about from the amazing 2 talks we just had earlier. This is one of the images that we saw earlier. And finally, question number 8, it's the International Space Station, a multinational project between the space agencies of the US, Canada, Europe, Russia, and Japan. And you can easily see it at night if you're lucky enough to find it. Okay, for the tiebreaker questions, there are around 158 currently known globular clusters in our Milky Way. And as I said, everyone did extremely well in this game. And we had 2 teams tied up for first place with 22 points. But finally, from the tiebreaker, we chose a winner, which is Exter. So congratulations, well done. We don't actually have your email, so if you could send an email to astronomyontaplighten@gmail.com or just send us a Facebook message to get in contact about your prize, that would be great. And other than that, I hope everyone enjoyed the games and see you next month. And now on to Lamine for the wrap up.
Thank you, Marta. And thank you everyone for sticking with us till the end. I hope you all enjoyed the 2 very interesting talks given by our speakers and the super fun game that was put together by our games team. If you'd like to attend more of such events, you can find out information about more Astronomy on Taps online in the link that is shown here. And with that, I have a very exciting news to share that we are coming back to the Burt at our next month's event that is going to happen on 31st of August. At that event, our speakers will talk about galaxies. And however, due to the COVID-19 social distancing protocol, there is a requirement of pre-registration. And you can find the link that is shown in pink here in the middle of the slide. You will also find the link in our social media channels. We'll post that soon. And the registration is open now and it will be closed until the required seat numbers are fulfilled. So we are very excited and we hope to see you all at our next events. With that, finally, I'd like to thank our speakers once again. Thank you very much for your talks. And you know, we usually give you these classes as a token of thank you. Unfortunately, we cannot do that now, but we will make sure that these classes find their way to you. And we also have a special thank you note to our team member, Robin. He is a master's student at Leiden Observatory, and he has been helping out for the last year. Currently, he is finishing his master's, and he is moving to University College Dublin to pursue his PhD. So many congratulations, Robin, and we wish you all the best from the Astronomy on Leiden team. And thank you very much for your help. And last but not the least, thank you very much to our entire team of Astronomy on Tap Leiden. We are currently only a few presenting in this online event, but of course it was not possible at all without the help of everybody in the team. So thank you all very much. And thank you everyone for joining us today. We hope to see you at our next event. Have a good evening.